Okay guys, let's continue our discussion, and sorry for interruption in the previous file. So we said that if A is a normal matrix, so then it is automatically diagonalizable. It means can be written of this form, U d U inverse. Okay, now what is the matrix U and what is the matrix D here? It is well known from the linear algebra, when U is a normal matrix, then when A is a normal matrix, then A has n orthonormal eigenvectors like U1, U2 up to Un. When we say orthonormal, it means the norm of each UI is 1 and they are mutually perpendicular. Okay, and of course because they are linearly independent, they form a basis for Cn, okay, n-dimensional complex Hilbert space. Then the invertible matrix U will be constructed like this. Let me show you. Okay, let me show you here. Okay, let me show you the matrix U to be the matrix with columns Ui. What does it mean? It means this. Let me show you. The first column U1, the second column U2 up to the nth column Un. Okay, and of course U is invertible. Okay, because the columns of the matrix U are linearly independent vectors. Okay, they are mutually perpendicular, so they are linearly independent. So therefore the matrix U is invertible. And then the diagonal matrix D is like this. Look at here. The diagonal entries lambda 1, lambda 2 up to lambda n are actually the eigenvalues of A. It means the elements of the spectrum of A. Then A can be written like this. A equals U d U inverse. We explained about U, and D will be this diagonal matrix, eigenvalues of A. Okay, now you suppose that, okay, so A is normal, is diagonalizable. Okay, it can be written like this. And suppose that F is a complex valued function of complex number such that F is defined on the spectrum of A. What does it mean? It means F of lambda 1, F of lambda 2 up to F of lambda n are defined. Okay, here makes sense. It means F of lambda I makes sense. It means F of lambda I is defined. Now we are going to define F of A like this. Okay, look at here. F of A, okay, A equals U d U inverse. F of A is defined to be, okay, U here, U inverse here. Look at here. F moves on diagonal entries. Look at here. These are diagonal entries. So F of A equals U, and here U inverse. Look at here. F of lambda 1, F of lambda 2 up to F of lambda n. So this is how we define F of A under those two conditions. A was normal, therefore diagonalizable, and then F is defined on the eigenvalues of A, on the spectrum of A. So we can define F of A. Now, for example, if F of Z is the square root of Z, okay, F of A, which is actually the square root of A, is defined to be, look at here, U inverse. Look at here, F moves on the diagonal entries. The square root of lambda 1, the square root of lambda 2 up to the square root of lambda n. Of course, it means F must be defined on the spectrum of A, which means eigenvalues of A. Then we can define F of A. And look at here, we have this property similar to what we have in ordinary calculus, right? The square root of A squared equals A. Why is it like that? You can see the calculation here. Let me show you. I prepared this with details. Okay, the square root times the square root of a, right? Okay, you can see here and you can see here. And here in the middle, u inverse u is the identity matrix, right? So it's gone. Now the product of these two diagonal matrices will be like this. So u, and in the middle. So what is this now? Look at here, like the square root of lambda 1 times the square root of lambda 1. So do you agree with me? This equals this. Lambda 1, lambda 2 up to lambda n. And what is this now? A. So you can see just like ordinary calculus we have this. So you can see that if t is a normal operator and f on the spectrum of t is defined as continuous, we can define this f of t for more general function, or it means that the functional calculus is working well, something like that. Okay, that's why we consider those two conditions. Now look at here. Next, we have a very important and interesting theorem. We just mention it without proof, okay? Because the proof is very complicated and it's definitely beyond the level of our class. So we just mention without proof, but we will give some example. Look at here. Let's say t is a bundle linear operator, normal, okay? T is a normal operator. Then the spectral mapping theorem says that if f is a continuous function on the spectrum of t. Look at here. What is this space? When you say C of a spectrum of t, the spectrum of t is a compact set. So this means the space of all continuous function complex value on the spectrum of t. Then look at here. When we define f of t is an operator. So definitely it has a spectrum. The spectrum of f of t by a spectral mapping theorem equals f of sigma t. It means the image of the spectrum of t under f. Very interesting. And this statement, look at here, if f belongs to C of the spectrum of t, it means f is a continuous function on the spectrum of t, and g is a continuous function on f of sigma t. Look at here, f is continuous function, right? So it maps a spectrum of t, which is a compact set, to a compact set. So f of sigma t is a compact set. So g is a continuous function on this compact set, okay? Then g of f of t, look at here, f of t is an operator, okay? Then you can define g of f of t to be another operator. This equals GOF of t. It means you can calculate GOF first, then you calculate GOF at t, just like what we have in ordinary calculus. Okay, so the proof is not required. Now, regarding the spectral mapping theorem, I'm going to give you one example. But okay, this one is not required. We don't need this. You can remove this. I'm not going to discuss. It is interesting, but it's not necessary. So you can remove this. But we are going to talk about this example. Okay, look at here. If you remember, we already talked about the unilateral shift on Hilbert space L2, and we already computed the spectrum of T, which is this. All scalars. Such that the absolute value of lambda is less than equals 1. Now look at here, we are given this function f of z equals 2iz, which is a polynomial of degree 1. Now we want to compute the spectrum of f of t, okay? We want to compute the spectrum of f of t. But let me mention something. You can see here, we want to apply a spectral mapping theorem, right? But in this example, t is not a normal operator, but still we can apply the spectral mapping theorem. And the reason is actually here is our function is a polynomial. Actually, when the function is polynomial, you can define f of t for any bundle linear operator. It doesn't matter, normal or not normal. So this is just some example to explain this spectral mapping theorem. Okay. Anyway, look at here. I've done here for you. Let me explain you. F of z is 2iz, right? Okay, sorry. F of z is 2iz, right? So f of t is defined to be 2it. Now, the spectrum of f of t, this operator, which is the scalar paradig of t, equals f of sigma t. Okay, and this is the spectrum of t sigma t. Now, look at here. If we take any element of the spectrum of t, like lambda, so f of lambda belongs to f of sigma t. But let me calculate the absolute value of f of lambda. The absolute value of f of lambda equals the absolute value of 2I lambda, right? Because this is f of lambda. And this equals, this is easy to see that this equals 2 absolute value of lambda, because the absolute value of I is 1. And since lambda belongs to the spectrum, the absolute value of lambda is less than equals 2, so this is less than equals 2. Sorry, the absolute value of lambda is less than equals 1, so 2 times 1, this is less than equals 2. So you can see f of lambda, the absolute value of f of lambda is less than equals 2. This gives us a conjecture about this f of sigma t. So you can see, if I take any element of f of sigma t, the absolute value is less than equals 2. So we claim that by this computation, that f of sigma t equals this set, all scalars such that the absolute value of lambda is less than equals 2. For convenience, let me call this set to be A. And regarding this claim, let me give you this picture. This is the spectrum of t, you can see. Look at here, the spectrum of t. All scalars such that the absolute value of lambda less than equals 1. What does it mean? It means interior and the boundary of this circle. Okay, sorry for interruption. So it means interior and the boundary of this unit circle centered at origin. Okay, and this is the complex plane. 1 here, this here is I. So we want to prove that the spectrum of f of t, which is equal to f of sigma t by a spectral mapping theorem, equals this circle centered at origin of radius 2. Okay. So let's do it. Look at here, to prove our claim, we have to show that f of sigma t is a subset of A, and A is a subset of f of sigma t. Here, you can see on the next page. We have to prove these two inclusions. But this one is clear actually. We have seen this. Look at here. When you say this computation shows that actually, look at here, each element of f of sigma t absolute value is less than equals to. So this computation shows that this inclusion is valid. It means f of sigma t is less than, is a subset of A. So we only need to prove that A is a subset of f of sigma t. Okay. So it means we have to show that each element of A, like alpha, belongs to this. So you take alpha belongs to A. Using this alpha, we construct lambda to be an element of a spectrum of T, like this. We take lambda to be 1 over 2I alpha, and 1 over I equals minus I. So this equals minus I over 2 alpha. We claim that this lambda belongs to the spectrum of T. Okay, why is it like that? If you calculate the absolute value of lambda, which is equal to absolute value of minus I over 2 alpha, this equals 1/2 times the absolute value of alpha, and since alpha belongs to A, the absolute value of alpha is less than equals 2. So this less than equals 1/2 times 2 equals 1. So you can see the absolute value of lambda less than equals is less than or equals 1. So definitely lambda belongs to the spectrum. So therefore f of lambda belongs to f of sigma t. But what is f of lambda? Let me calculate. F of lambda equals 2I lambda. Equals 2I, and this is our lambda, and this is easy to see that this equals alpha. So f of lambda actually equals alpha, right? So alpha belongs to f of sigma t. Of course, here I wrote sigma f of t. Of course, by spectral mapping theorem, sigma f of t equals f of sigma t. So you can see each alpha in A belongs to f of sigma t. Okay, of course these two are equal by spectral mapping theorem. So this is true. Okay, this is true. Okay, this is true. So this shows that these two are equal. So it means we have the spectrum of f of t, which is the equal to, by the spectral mapping theorem, equals f of sigma t equals this. Okay, so it means this is true. This is the spectrum of f of t. So do not forget, here you can see when we say alpha belongs to sigma f of t, actually this sigma f of t equals f of sigma t. Okay.